Alrighty, we have some identities that you all need to memorize. Let's go through some of these. Sine of an angle is equal to 1 over cosecant of the same angle. What that's saying is that sine and cosecant are reciprocals. This one underneath of it, cosecant of A equals 1 over sine of A, that's also just saying that cosecant and sine are reciprocals. Same can be said about cosine and secant, they're reciprocals, and tangent and cotangent, they are also reciprocals. Just real quick, just make a note here. Pardon that. Let's make a note that if I were to square sine of A, we could write it like this. That's sine of A, and then when you're done, square it. A more common way to write this would be sine of A squared. It means the same thing with the parentheses, but the squared is right after the n in sine. This is also true for any of the other 5 trig functions. What this does not mean, it doesn't mean sine of your angle squared. It means take sine of your angle, when you're finished, square it. Looking at the quotient identities, tangent of an angle is equal to sine of the angle over cosine of the angle. It's a fact you have to memorize. Comparing that to cotangent, if you see up here once again that tangent and cotangent are reciprocals, then it makes sense that if tangent is sine over cosine, cotangent is the reciprocal cosine over sine. Going down to the Pythagorean identities, these are called such because they are derived from the Pythagorean theorem. Sine squared of an angle plus cosine squared of an angle equals 1. Another fact, tangent squared of A plus 1 equals secant squared of A. And the final Pythagorean identity, 1 plus cotangent squared of A equals cosecant squared of A. You must memorize those identities. Then we have a bunch of these properties from algebra. Just a quick review. Addition properties, they're called that because it works for addition, also for subtraction. The commutative property says if you add 2 things together, such as 2 plus 1, that's the same as adding 1 plus 2. Associative property says if you're adding 3 or more things together, you can add them in any order. The additive identity, which is 0, says that if you add 0 to anything, you get that same number back. The additive inverse property says if you add a number and its inverse, it will always equal 0. Looking at the multiplication properties, it's called that because these works for multiplication. The commutative property says if you multiply 10 times 1, that's the same as multiplying 1 times 10. When you multiply 2 things together, you can do it from left to right or right to left. The associative property says if you're multiplying 3 or more things together, you can do so in any order. The multiplicative identity is 1. Multiplying 1 times anything gives you that thing back. X times 1 is x. Multiplicative inverse property says if you multiply a number, x, by its inverse, 1 over x, it always equals 1. These properties of equality for real numbers, that is basically just saying these are things that work for any equation. You've used all of these things millions of times in your life, figuratively. Multiplication property says if you have an equation, you can multiply both sides of the equation by the same thing. The addition property of equality for real numbers says if you have an equation, you can add the same number to both sides of the equation. The distributive property says that if you're adding 2 things together and it's being multiplied times something, you can multiply the x times each term in the parentheses. The reflexive property says that any number is equal to itself. The symmetric property says if you have an equation with a left side and a right side, you can write the right side on the left and the left side on the right. So in other words, 3 equals x. That also means x equals 3. Transitive property, if x equals y and y equals z, then x equals z. Basically, the common thing here is this y, those are in the middle. And since they're both equal to an x and a z, that means x and z have to be equal. Substitution property says if you have two things that are equal, you can replace one of those things with a thing that is equal to it. The root property says if you have an equation, you can take an even or odd root of both sides of the equation and it's still true. If you take an even root, make sure that you use plus or minus. Exponential property says if you have an equation, you can raise both sides of the equation by the same power and that equation is still true. Now let's check out our first example, example A. Solve for values of theta between 0 degrees and 90 degrees. 0 degrees and 90 degrees means it's in quadrant 1. So this problem is telling us we are in quadrant 1. I have some instructions here on the side that we're going to try to follow that will guide us through this problem. Draw a reference angle in quadrant 1. That's pretty easy to do. A reference angle is formed by the terminal side and the x-axis. So theta is here. That's the reference angle. Then it says make a right triangle. When you make these right triangles, you always do so that one of the legs in the right triangle is on the x-axis. Sorry, I had to pause that. You probably couldn't tell. My daughter stepped on a toothpick and she was screaming bloody murder. Where was I? So we made a right triangle. Make sure one of the legs is with the x-axis. If needed, find the length of the third side of the triangle using the Pythagorean theorem. Let's see if that's needed. We are told here that tangent of theta is 3. Tangent of theta is 3. 3 we could write as a fraction, 3 over 1. Tangent is always y over x. That means that x in this triangle is 1 and y in this triangle is 3. We're supposed to figure out what cotangent of theta is. Cotangent of theta is x over y. That would be 1 over 3. Since we don't have to figure out what r is for this problem, because cotangent doesn't have an r in it, we can stop, and the answer to this question is cotangent of theta is 1/3. This entire problem could have been done with no work. If you recognize that if tangent of theta is 3, cotangent of theta is its reciprocal, because tangent and cotangent are reciprocals. Therefore, cotangent of theta would be 1/3. Let's go to number 2. If sine of theta is 5/13, find cosine of theta. Well, let's figure this out once again, just how we did the last one. I'm going to do this in slightly different order. Sine is y over r. So y is 5 and r is 13. We're supposed to first make a reference angle in quadrant 1, calling that theta. Then we make a right triangle, making sure that one of our legs is on the x-axis. Y is 5, r is 13. We're supposed to figure out what cosine of theta is. Cosine of theta is x over r, but we don't know what x is. Using the Pythagorean theorem, x squared plus y squared equals r squared. You can substitute in for y with 5. When you substitute, use parentheses. And for r, we can use 13. 5 squared is 25. 13 squared is 169. If you subtract 25 from both sides, you get 144. Square rooting both sides, you get x is plus or minus 12. In quadrant 1, your x values are positive. So this is positive 12. Therefore, cosine of theta is x, which is 12, over r, which is 13. 12/13. Question 3, if cosine of theta is 2/3, find tangent of theta. Well, once again, our theta is going to be in quadrant 1. It's a reference angle. We'll make a right triangle, making sure that we're using the x-axis. Cosine is x over r. Therefore, x is 2 and r is 3. Tangent of theta is y over x, but we don't know what y is. Using the Pythagorean theorem, we can figure out what y is. X is 2, don't know what y is. R is 3, 2 squared is 4, 3 squared is 9, therefore y squared is 5, which makes y plus or minus the square root of 5. Quadrant 1, y is always positive. Therefore, tangent of theta is y, the square root of 5, over x, which is 2. Part B. Express each value as a function of an angle in quadrant 1. In quadrant 1, all the angles are between 0 degrees, not including, they're all between 0 and 90 degrees. So an angle in quadrant 1 has to be acute. So let's figure out how we can do this. Here's some guidance here. If you need it, you may want to add or subtract multiples of 360 degrees to find a more appropriate coterminal angle. In other words, if the angle you're given, in this case 400 degrees, is not between 0 and 360 degrees, you might want to choose a coterminal angle. So you can find it easier in the coordinate plane. You don't have to do that, but you might want to do that. To find a coterminal angle, coterminal means that they have the same terminal side. Coterminal sides are always complete revolutions apart. One revolution is 360 degrees. Therefore, a coterminal angle to 400 degrees is 40 degrees. Sine of 40 degrees and sine of 400 degrees are the same thing. Then it says find the reference angle and draw a right triangle, just like we did for example A. So this is in quadrant 1 because it's 40 degrees. So our reference angle is 40 degrees. It's formed by the terminal side and the x-axis. Then label the x, y, and r values with positives or negatives. Well, in quadrant 1, the x value is always positive. The y value is always positive, and the r value is positive no matter what quadrant you're in. So to answer this question, what is sine of 400 degrees as a function of an angle in quadrant 1? This is easy. You take the reference angle that you just found, which is sine of 40, and then you determine, is this a positive or negative answer? And that depends on what quadrant you're in. Sine is y over r. And we're saying that in quadrant 1, y is positive and r is positive. If you divide two positives, you get a positive. Therefore, the answer is positive sine of 40 degrees. To sum up, for these kind of problems, you have to determine if it's a positive or negative answer, and you have to determine what the reference angle is. Once you have those two things, then you have your answer. Let's check out example 2. Number 2 is tangent of 475 degrees. Once again, if you find it easier, you may want to find a coterminal angle. You may want to do that whenever the angle you're given is more than 360 or it's less than 0. Coterminal angles are always complete revolutions apart. One revolution is 360 degrees. 475 minus 360 is 115. So tangent of 475 is the same as saying tangent of 115 degrees. So where does 115 degrees fall in the coordinate plane? It's in quadrant 2. We need to know the quadrant, and we also need to know what the reference angle is. The reference angle, once again, is formed by the terminal side, which is this diagonal, and the closest part of the x-axis so that it makes an acute angle. That would be this part here. So our angle is going to be 65 degrees. That's our reference angle. How do you get 65? Well, if it's 115 degrees to this terminal side, and it's 180 to the negative x-axis, that means this is going to be 180 minus 115, which is 65. So we know our answer is going to be tangent of 65 degrees. Now the question is it positive or is it negative? That's what we have to determine. Let me rewrite 65. It's pretty ugly. In quadrant 2, your x value is always negative, your y value is always positive, r is positive in every quadrant. Tangent is y over x. That's a positive over a negative. If you divide a positive by a negative, you get a negative. So this answer is negative tangent of 65 degrees. Number 3, we have 220 degrees. There's no need for a coterminal angle because this is between 0 and 360. 220 falls into quadrant 3. So we draw our terminal side. We make a right triangle with the x-axis. It is always with the x-axis. If it's 180 degrees to the negative x-axis and it's 220 to our terminal side, that means that we pass this negative x-axis by 40 degrees too much. In other words, 220 minus 180 is 40 degrees. So our answer to this is going to be either plus or minus, not sure yet which one, cosine of 40 degrees. That 40 degrees is the reference angle we just found. In quadrant 3, x is negative, y is negative, r is positive in every quadrant. Cosine is x over r. That would be negative divided by a positive, which is negative. So this is negative cosine of 40 degrees. Example C. Write an expression for each of the following in terms of the given function. Number 1 says secant of theta in terms of cotangent of theta. When you're finished with this problem, it will say secant of theta equals, and the other side of the equation, the only trig functions that you can use are cotangent. There could be many cotangents, there could be just one, there could be many numbers. So once again, you're done when secant of theta is by itself, and the other side only uses cotangent and other symbols or numbers. So if there was an identity that used secant and cotangent, we would use that one, but there isn't. What we can do, though, we can use secant squared of theta equals tangent squared of theta plus 1. This is one of the Pythagorean identities. The reason I chose this one, and there's many that you could choose to start with, because this already has secant almost by itself, it's just the squared is here. And although the right side doesn't have cotangent, it has tangent, which is closely related to cotangent. To get secant by itself, you could simply square root both sides of the equation. That would give us secant of theta, and on the right it would give us plus or minus the square root of tangent squared of theta plus 1. Now, theoretically, we're halfway finished. We have secant of theta by itself. The right side has to be in terms of cotangent, and it's currently not. Fortunately, there's an identity that says that tangent and cotangent are reciprocals. Therefore, tangent squared of theta is the same as 1 over cotangent squared of theta. And instead of me just writing plus 1 here, I'm going to have to add this 1 to the 1 over cotangent squared. So I need common denominators, so I'm going to change that to cotangent squared of theta over cotangent squared of theta. The reason I have to do this, I have to add these together, we have a radical. When you have a radical, you're not allowed having a radical on the bottom. In other words, you can't have fractions inside your radicals. We have fractions. So we have to fix this. Once you have common denominators, you add the top numbers, 1 plus cotangent squared of theta. Can't add the bottom, because if you have common denominators, you just write the denominator once. Now we're getting closer. When you square root a fraction, you square at the top and you square at the bottom. So it's going to be 1 plus cotangent squared of theta in the numerator, and it's the square root of cotangent squared of theta in the denominator. Now this numerator is not a perfect square, so we can't simplify it. We just leave it as 1 plus cotangent squared of theta. Our denominator is a perfect square. The square root of cotangent squared of theta is cotangent of theta. Therefore, we have set out what we were supposed to do. The left side is just in terms of secant, and the right side is just in terms of cotangent. So it's secant of theta equals this hot mess here. Let's do another. Number 2, we have cosecant in terms of cosine. If there was an identity that used both of those things, we would want to use it, but there isn't. Something that's closely related to this is sine squared of theta plus cosine squared of theta equals 1. It's closely related because it has cosine in it, which we're supposed to have, and it has sine in it, which is the reciprocal of cosecant. So let's change the sign so that it's cosecant. That would be 1 over cosecant squared of theta plus cosine squared equals 1. If we get the cosine, I think I said cosecant. This is 1 divided by cosecant squared plus cosine squared of theta equals 1. If we subtract cosine squared of theta from both sides using the subtraction property of equality for real numbers, we get this. And then we're trying to get cosecant by itself. Right now it's on the bottom of a fraction. So if you multiply both sides by cosecant squared, on the left side the cosecant squared and the cosecant squared cancel. On the right side you get this times cosecant squared. Trying to get cosecant squared by itself, once again, if we divide both sides by 1 minus cosine squared of theta, we get 1 divided by 1 minus cosine squared of theta. And then to get cosecant by itself, square root both sides. That would be plus or minus the square root of 1 over 1 minus cosine squared of theta equals cosecant of theta. Now the right side's finished. It's got just cosecant of theta. That could be on the right or the left, it doesn't matter. Left side's not finished because we have a fraction inside a radical, and the radical can only be on the top of a fraction, can't be on the top and the bottom. If we square root the top and the bottom, like so, I am running out of space fast. The square root of 1, of course, is 1, and the bottom is not a perfect square. But we are not allowed to leave this so that we have a radical on the bottom of a fraction. It's called an irrational denominator. We have to rationalize it. To fix it, if we multiply the bottom times itself, so if we multiplied the bottom times 1 minus cosecant squared, if you multiply it by the bottom, you have to also do it to the top. It's essentially saying we're multiplying this by 1, because anything divided by itself is 1. So how does that help us? Well, it's going to make this plus or minus the square root of 1 minus cosine squared of theta over, on the bottom when you multiply something by itself, you're squaring it. The square and the square root cancel, so you get 1 minus cosine squared of theta, and of course this is equal to the right side, which hasn't changed, which is cosecant of theta. That finishes that problem. We're done because we have cosecant of theta by itself, and it's in terms of cosines only. There's no other trig functions on the other side. Example D is supposed to simplify this. There are literally a million different ways to do this problem. And by saying a million, what I really mean is there is an infinite number of different ways to do this problem. Simplify means to make it more simple. So how can we do this? Well, there's lots of ways that you could do it. I recognize right now that cosecant squared of theta is in one of the Pythagorean identities. I want you to look at that real quick. I believe it's the third one, which says that cosecant squared of theta is the same as 1 plus cotangent squared of theta. If I bring down the original minus cotangent squared of theta, you're probably thinking that doesn't make it more simple, that makes it more complicated. That's true. But watch what happens now. We are adding and subtracting cotangent squared of theta, which means they cancel, which leaves us with equals 1. So we're finished. It equals 1. You could have done this problem in lots of different ways and got the same conclusion of 1. It doesn't matter how you do it, as long as you use the properties properly, and you get it simplified to the same thing. Number 2, I recognize right away. Well, let me tell you something that you can't do. Some people want to do for this problem. Some people would say, well, I have a cosine squared on the top and bottom of the fraction, so I can cancel those. That's a false statement. It's false because of this plus sign. If that plus sign wasn't there and it was multiplication, then you could cross those off. But it's addition, so you can't. The first Pythagorean identity, sine squared of an angle plus cosine squared of an angle equals 1. So you can replace that numerator with 1. 1 divided by cosine of x is secant. Therefore, 1 divided by cosine squared of x is secant squared of x. This problem is completely simplified. Number 3, cosine of y times cosecant of y. It appears as though this could not be simpler than it already is. But it can be. Sometimes the best thing to do for these problems is to take anything that you can and make it in terms of sine and cosine. For example, cosine is already in terms of cosine. I'm not going to change that. Cosecant of y we could make 1 over sine of y. And once again, this doesn't appear to be helpful because we just made the problem more complicated. What happens when you multiply a whole number, cosine, times a fraction, 1 over sine? We multiply the whole number times the top only, and leave the bottom the same. So this would be cosine of y over sine of y. You're probably still thinking, that doesn't make it more simple. Well, you're right, but this next step does. Looking at your quotient identities, the second one, cotangent of y equals cosine of y over sine of y. Therefore, we can replace cosine of y over sine of y with cotangent of y. So it took several steps, but we started with 2 trig functions, ended up with 1. So this whole thing is your answer, and we simplified it to cotangent of y. Number 4, tangent of z divided by sine of z. This is another one of those problems where it's probably best if you change everything so it's in terms of sine and cosine. Well, tangent of z, we could make that sine of z over cosine of z. Sine of z is obviously already in terms of sine. Another option that we could pursue here is simplifying this complex fraction, and there are lots of ways of doing this. One such way would be to say, I don't like the fact that I have this sine divided by cosine. Well, how do you get rid of dividing by cosine? Well, you multiply by cosine. You can't just multiply a fraction by cosine of z, it's going to change its value. So you could multiply the top and bottom of this by cosine of z. That's the same as multiplying by 1. How does that help us? Well, if you're multiplying and dividing by the same thing, it cancels. Which then gives us sine of z divided by sine of z times cosine of z. Well, sine divided by sine is 1, which makes this 1 over cosine of z. 1 over cosine of z, that's the reciprocal of secant. So this simplifies to secant of z. That's as simple as this could get. I'd like to remind you once again, you can do these problems in lots of different ways. Don't think this is the only way that you could have done that problem. Looking at number 5. This is another problem where if you change each identity into terms of sine and cosine, it's going to make it pretty simple. Lots of other ways to do it, but it's one way that you could do it. Tangent of A is the same as sine of A divided by cosine of A. That's a quotient identity. Cosecant of A is the same as 1 over sine of A. That's one of the reciprocal identities. We are multiplying our numerator and denominator by sign, so they cancel, which leaves us with 1 over cosine of A. Looking at your reciprocal identities, 1 over cosine of A is the same thing as secant of A. To sum up these problems in example C, just tell you a few things. 1, you are going to get frustrated. 2, if you have the identities memorized, you are going to be frustrated less than you would be if you didn't memorize them. You'll get the problems done more efficiently, and you will spend less time on your homework if you first memorize all the identities. Another thing that I would like to tell you is if you get stuck on one of these problems, and you may get stuck on the first step, here's my advice, and it sounds insane. If you don't know what to do something, anything. There's a good chance that will lead you to something else, and before you know it, the problem is done and you have no idea how it was finished. And the last thing, once again, is a lot of these problems, if you change the trig function so it's in terms of sine and cosine, the problem kind of works itself out naturally. End scene.